Hello, and welcome to this video, which is a video among the series for linear algebra to understand the quantum mechanics. In this video, we will extend further from the last two chapters that we have seen numbers and the complex numbers along with the properties of complex number, and we will extend it to now relevant vector calculus. What is a vector? It's a two-dimensional complex entity which has a direction, dimension, and the magnitude. Elements of vectors helps you to decompose it in dimensional axes, for example x, y, and z axis, and they are written as V having an arrow above it with the elements being marked in a matrix form like V1 and V2, where the elements can be part of the vector plane and they belong to the complex number category. Here in this example, you see that the vector v has two elements, and that's why they are two-dimensional in nature. For the programming purposes, the indexes of the vectors start from 0, while in the mathematical notation is start with 1. The complex vectors of any dimension, so they can hold any number of elements in it. The example which we see here can run up to n, where n can be any number in the natural category. And all the elements, again, as said before, may belong to the complex plane, where the dimension of that plane could be n. There are mathematical operations which are possible on vectors. For example, vectors can be added, and it is done by piecewise addition of the elements. So each elements add to the same element on the position with the other vectors. So the example that you can see here, that the first element of vector u can be added with the first element of vector v, which result in the first element of vector w. Another operation that is possible on vectors is to multiply with the scalars. For example, a scalar which is of a complex number form or in part of the complex number can be added, can be multiplied, all the elements of a given vector. So the vector 2i in this example is getting multiplied by all the elements of vector u to give vector w. Keep this information as noted that when I square, when we have an I square, I multiplying twice with itself, making it I square, that the value translate it to -1, as we have seen in the definition of complex numbers. There are various norms that has been defined for the vectors. The first and the most simplest is the L0 norm, which represents all the non-zero elements in a vector. So for example, if you see here, a vector has two elements 1 and 2. So the L0 norm is 2. What does L0 norm represent? It represents all the active dimensions a vector is in. Extending to L1, it's an sum of the absolute values of all elements. So for example, if the vector element is negative, the absolute value of that element will be turned into positive, and that's when all the numbers are then added to give you an L1 norm. Looking at the example here, you see that there are two elements 1 and -1. The absolute value of -1 will turn out to be 1, and if you add those two numbers, you will get 2. What does L1 norm actually represents is the actual distance of the vector on each of the given axes. Moving on to L2 norm, which is Euclidean distance, that is the straight distance from origin to the point of the vector, and it is given by the formula of under root of elements square added upon. So if we look at the example here, the vector has two elements 1 and -1, which is then added as a square and has been taken as an under root. So the answer is under root 2, and the L2 norm is a direct distance, therefore representing the magnitude of the vector. It is important to understand that studying a vector in a complex plane can be very tricky. Therefore, normalization, that is the art of making norm equal to 1, a unit vector, and to understand the concept, thereby preserving the direction of the vector, is very important. How do we normalize? Divide all the elements by its LP norm, which means, for example, if p is equal to 1 when we are L1, then take the absolute value for the L1 and divide each element of the vector with that value. It is important to note that an L0 norm, which represents the number of active elements, cannot be normalized, whereby we assume that the vector is a non-zero vector. This is the example. Here you see two elements. You calculate the norm, the L1 norm. You got the value as 2. Remember that the negative value becomes absolute, so that's why it becomes positive. So 1 plus 1 is 2. And then you normalize the vector by dividing each element with the value 2. Same can be extended for p is equal to 2, where you follow the same procedure, but it's a L2 norm, so you will have to take the square root of all the added values. That's why you see the difference. In the first case it is 1 by 2, and in the second case the elements is 1 under root 2, because they are differentiated between L1 and L2 norm. I'll stop here. I hope you enjoyed the video and I hope to see you in the next one. Thank you very much.